Okay, good morning everyone. Thanks for coming. This Severo Ochoa colloquium will look east. It will have a look at what China has been doing. I think most young people here are quite used to the idea of China as an economic superpower, but it hasn't always been like that. The older people will remember that China has come a long way economically in the last 20 years or 30 years. And scientifically, we've witnessed China going from a country with some tradition but no major frontier projects to a country that is ready to take on the competition with CERN openly. We'll hear about both things. We will hear about this project that they have, the CEPC, a circular collider that could be the new center of particle physics. But we'll also hear how China got there, how China got to the point where it could propose such a project. The speaker of today is Professor Yi Gao of IFIC in Beijing. He was trained in Europe. His background is actually in Lille, in Orsay. He's been in Europe for a long time. But now he's in charge of both the design of the Chinese machine, the CEPC, and he's a very important player in the Chinese participation in other future collider projects. I think he's the perfect person to tell us what Chinese plans are, what we can expect in the next decades. Thank you for coming, and the floor is yours.
Okay. Thank you very much. So, thanks Marcel's introduction, and thanks for the invitation from Juan and Marcel for me to come to this prestiged institute. So I have been here, I think, twice, or anyway, this first time for me to stand here to give a lecture, to give a seminar. So today my seminar is mainly two parts. The first one is the first CEPC project, like background, very quickly for you to, because you already know, most of you already know. So, but this is to give you a goal, scientific goal and project goal. And mainly is this is the task by Juan and Marcel on the second part. That means how and what is the possibility and what is the background. You can handle this in terms of economy, scientific ability, international collaboration. All these questions I try to provide this kind of answer by data and by background information. So I try to provide as much of information in the PPT. So maybe sometimes I'm quick, sometimes slow, but you can analyze it later as a piece of document later. So this is the main, idea for me to present. The voice is okay?
I don't think so.
You don't think so? Now it's better? Higher?
Yeah, broad.
So the background people, okay? So I will speak louder.
Yeah.
Okay. I try to cover this the status, the R&D, citing, and mainly is this part takes time. So about CDR status. So this is the machine looks like. It's a circular one for its factory, and this is a physics goal. That means 10 years we want to produce 1 million of clean hits. So this is the first goal for the Higgs factory. And at the same time, this machine, since it's circular, it can work at the W and the Z. For the TD bar, I don't talk about it, but for 100 kilometer, in principle, it's okay, but I don't talk about it. And later, this machine, the same tunnel, after running 10 years, say, 10 years of electron-positron collider, in the same tunnel without dismantling electron-positron collider, we put the SPPC, proton-proton collider, in 100-kilometer ring. That means this energy will around, depending on the magnets, around 100 TeV, around, depending on the magnet strength. So this is the rough scientific goal. This is not my talking the concentration. The concentration is actually how to realize it, both technically and economically. So in terms of the accelerator design goal, we have 2 IP, and the luminosity for Higgs is 10^34, bigger than that, and also for the Z is higher than this. Usually it's 10 times higher than these 2 IPs. So the polarization in this stage, we don't think about that, but in the, in the TDR phase, we are thinking about polarization for the energy measurement for full polarization. So this it needs to be added to the TDR. In the CDR, we have only 3 pages for the simple analysis. So this is 5 system. We have the 10 GeV VNAC, 10 G.
Change the side.
Yeah, you're right. So we have 10 GeV VNAC. 10 GeV compared with 120 is quite low. Be careful, it's very low, but if it's higher, it will be very expensive. But anyway, 10 GeV and injecting the 200 kilometer booster. In the same tunnel, we will have 2 ring, the collider ring. They are here, the collider ring booster, and this is SPPC later. So we need to work on these, and also detector. So for the design, we have since 2012 here, the first parameter we proposed, that means 2 months later and 3 months later after Higgs was found. The idea was proposed in September, 2 months later from Higgs discovery. And then we go through a road design very light type until these 2 full part ring. That means this part have a double ring, but this is a single ring. We put RF. RF the same for electron and positive. So this is baseline. So today, I'm not, mainly is not to introduce accelerator design, I just go through the accelerator. So this is IP region, the final focus region. So all these final focus is very similar to linear collider. So it's very different from the existing collider, even lab. So lab is a simple machine. You have you just squeeze your beam to collide, and you don't have many complicated optics to make this very small beam size. Remember, the beam pipe of the lab is big like that, 111 millimeter. But for this advanced collider, your beam pipe in the detector part is only 30 or less than 30 millimeter. So this is the difference. Of course, the luminosity here is 100 times, more than 100 times than that. So this is a LINAC with a damping ring, and this is a booster. So we had a progress from this pre-CDR, single ring pre-CDR, which doesn't work because no dynamic aperture. If we want this luminosity, there's 0 dynamic aperture. So we go to the advanced, the progress report in this last year, and that gives documentation to why we choose the final baseline. So all documented here. And then this is the final the CDR, which is released for accelerator part. For the detector part, it's finished in September, and Marcel was the committee chair of the detector part of the CDR of CEPC. So this is the site you can download. So we have the international review for accelerator, and Marcel is the committee for Marcel is the chair for the committee for physics detector. Here is Oide-san at CERN now. He is the chair for this one. Okay, so the conclusion. The conclusion is that The committee believes that CDR has already reached a sufficient level of maturity to allow approval to proceed to technical design, TDR. So this is the parameter. I will not go to the details. So you see the luminosity is 3 and 34, and the W is 10, and the Z is 16, 10 to 34. And if 2T, if this is detector solenoid field, it can reach 32. So this is the whole lattice of the ring, and this is RF. This for the Higgs, we need 242 cell cavity, because here we have RF people, and this is 2 cell, 652 cell for almost 300. So each cryo module will have 6 cavities. I will show you later. So this is the booster. Booster is IOC type structure, 1.3 gigahertz, and the 9 cavities in 12 meter long cryo module. So this is the booster extraction, and this is the booster optics. This is the booster RF, the 1.3 gigahertz Tesla type, 100 cavities. This is cryogenic systems. We need about how many? We need 4 stations and 4 big ones, 18 kilowatts at 4K. This is the LINAC. So this is designed, and this is the requirement. So fulfill the requirements. This is S-band. So we also propose as a backup. For the height to raise the energy from 10 GeV in the LINAC to 45 by plasma acceleration. So on paper it works. So we will allocate the 8 million in the next several years to test this idea. So this is the detector. You see L star is 2.2, and this is the crossing angle. And if you multiply these two, this is the same separation as Super K. So this is technology determining the separation, because your semiconductor protocol, you cannot be too small because you cannot too big. Mechanically, you cannot be small. So this is the same order magnitude Super K and FCC. So this is the field is 3 Tesla, and FCC is 2 Tesla. So maybe later, how to say, if 2 Tesla, the detector will have some changes, but from actuator point of view, we are welcome because we can have a higher luminosity. So this is the MDI design, superconducting magnet. This is the civil engineering, and this is there are many the companies work with us on the civil engineering design, including the detector hole, all these things. This is the detector. About the power, so this machine is circular, so it spends more power, uses more power than IOC. IOC for the same energy, it uses only 100 megawatt. Here we use 300, so you see a factor of 3 AC power. So this is the difference. But another difference is IOC is 250 RF. I mean, energy is accelerating. All these superconducting, but CEPC, we need only 2 GeV superconducting machine. So we have a very small superconducting machine compared with this 250. So this is a 100 factor of 100 RF system. So this is the cost sharing. You see, without detector, annual detector is a small portion of that. Without detector, this is mainly civil engineering, and RF is only 6%. The magnet is here, vacuum is here. So this is not the point I want to show you. So I just show you that this is the how to say the timeline. We want to start from 22 construction till 30. So this period now we're here. In the next several years we want to make R&D to finish so-called the TDR. after TDR means there's no technical obstacle. But for the moment, we cannot say that. So this is the RF, you see, like that. And this is for booster RF, C type. And this is the new technology breakthrough this September. So for the EP, this big EP, for many frequencies is okay. The cavities and this cavity inner surface repairing system and T mapping and also other things. Also, this is cholesterol. So the first high efficiency cholesterol. In the first version, maybe it's not cholesterol not so high, but this is the first one for CEPC of this kind. It's 800 kilowatts. So we're fabricating it. So the next year we will have the first piece of it. Later we'll progressively to reach the goal is 80% efficiency because this is important. Imagine if this is 70 and 80, the AC power, the difference is quite big. So we want high efficiency cholesterol. So we work with the industry and another institute. We have a network, work on that. We have budget. So now the people are fabricating it now. So this is the cholesterol in the tunnel. You can see all the magnets. So it's two beam lines, so separated by 35 centimeters. So these magnets are same piece, but two passages. So of the dual magnets, both for dipole and the quadrupole. But the sextupole, they are independent. They are not in the same. Not for the same pipe. This is the same block, 2 pi, also here. This is for booster magnets. Booster magnet is very special also because boosters start from 10 GeV, the field starts from 30 Gauss. So the straight field now here is about 0.5 or 1 Gauss. In the tunnel, maybe 2 Gauss. Anyway, the field for the booster to start left is 30 Gauss. It's very low. So we need a very special design of precisely. The most difficult, in fact, is this dipole. Surely this is the bottleneck, and we have other solutions and backup for this. And anyway, we have to study it as a technology bottleneck. So this is see the booster magnets, and this is the dipoles for the main collider, and this is the quarter. For the MPI, they're very complicated also. So you have to connect your MPI. This inside is a protocol, magnetic protocols. You have to connect this one. There is a flange. Inside the detector, this is a beryllium pipe, which is smaller than that, but you have a flange. So you have to connect them without the hand can touch it. So you have to remote, like Super K. Super K is doing like that. Also the alignment here. The alignment is, this is very heavy and long. But the precision is in the order of micron. So you have to, so these mechanics, we are working on all these with a company. I put the company name here. So this about site, we have for the moment 6 sites, and recently we have other places ask us to go there. And so we have the north, to the west, to the east, to the west, and in the middle, and in the source. For example, this is in Guangdong, face to Shanghai, Hong Kong. For example, the geography is okay. The temperature is different. Here is the coldest, 6 degrees, which is good for AC power. And this is, of course, every 20. So because 300 megawatts, you run it, you need to cool it down, and so you need the big. I think the difference between here and here is 50 megawatt electricity for cooling to make it go up and to keep this oscillation. So extra 50 megawatts. Here maybe in between. Okay, so this is Also, another important thing, so CIPC, the CEPC, the Industry Promotion Consumption, they are very helpful. I mean, now we have already 67 companies. They are public companies, they are private companies. They helped us a lot. I put the domain here. They are working with us. So they MDI for magnets and for vacuum chip and for many things. They are and for civil engineering design and siting. All these they participate. And also we have a document system. We are just already almost ready to start. That means with this document we can make a remote collaboration. Imagine both inside, within IHAB, different laboratory, and even with outside international laboratory, they can share the document by giving their password. They can at any level to exchange file and to discuss online. So this is a so-called project-wise program, which is widely used in industry, and they are helping us to. So now I go to the main part of this talk. That means the goal is quite ambitious. It's 100 kilometer, say more than around 5 billion. So $1 project. So and also the timeline is very short. So it's quite challenging in terms of budget, for human power, technology, in terms of many things. So how can this project be possible in terms in the environment, of course, in the international collaboration? This is the question, and I'm asked to try to provide some basic and background information to that. So here I collected some information for you on this. So see, this is the economy status the last year. So the China is this number, which is the second after US. You see US is 24, China is 15, and Japan is 6. So this is more than double, and also other countries here. This is European countries, Europe. So this is give you, this is so-called this GDP, and we know that this is roughly China where economically it's located. And about the R&D investment, you see that the R&D divided by GDP for the main countries in the world in the 2 years before, China is here. So about two, two. This year is 2.5, but this is average of whole China. So you see the advanced country, in average of this country in advance, they reach the 4%. And China, only a few cities reach the 4, like Shenzhen. I will show you the city. So in average, 22%. This is 2.5. And this number increase because you want to know the speed of change of this curve, not only today value, but so you see from 2010 is 1.7, and this year 2.5. And I personally, I believe next year this number will increase also in the national, because our goal is to increase about 4%. So we still have room to go like that. But this curve is quite, how to say, this curve is quite significant, and we can imagine later. I think the speed of the curve will be higher than in this part, personally I think. So the RF, you see, you can find the R&D fund for different regions is different. So some cities can reach very high. I mean, Beijing is quite high. It's 6%. Shenzhen, I think, And Guangdong is, Shanghai is this one. Guangdong is here, but Shenzhen is a city of Guangdong, but Shenzhen itself is genetic, recent news of this genetic Drew matter is coming from Shenzhen city. Their R&D is in the order of 4%. So you see the China is not uniform, and some places economically it's not so good, but some places is good. For example, Shanghai, they support the XFEL project. It's a Shanghai. It should not be these provinces, because Shanghai economically they are more powerful locally. So the total number of the scientific human resources, this is 10K, 10,000. This is the 10,000, and you have different things. This is the total number of scientific human resources in the number of 10,000, and it's here. You see it's increasing from 2,000 and to here. So you multiply these by 10K, you got the whole China scientific people, R&D people, the science and the technology people. And this one is the university. This is the people who has a university above the university level. So this is a number, it's roughly to give an idea of how many people in China working on science and technology as a whole, and increasing with year. So this is the R&D. The country. This is the countries with R&D people number over 100K. So this number doesn't matter too much, but you can see that this is the country, and this is the year is almost the same. And this is the R&D person number per year. And this is the R&D. This is the you can compare with other country of these numbers. So this is the evolution of China's SCI scientific publication number and the ratio with respect to that of the world. So you see, in 2000, not 2 years before, China's publication is less than 20%, 60% of the world publication. So it's the ratio is quite, and this is the absolute number of publication number of SCI as a whole country in every field of SCI. So this is the evolution of China's SCI publication ranking in the world. So you see, in 2006, the ranking is 5th in the world, and in around where it's 2009, China is already ranking the publication. So till now, still number 2. And this is the evolution of China citation number ranking in the world over the last 10 years. So this is citation. So you see in the modern ranking 13, and now it's 2nd. And the ranking of countries, publication number more than 200,000, and the average citation during the 10 years. You see the first is the US, China, England, Germany, and this is the publication number, ranking, citation. Okay. So this is correspond to roughly the status of economy position. It's a so-called the second. So this is the China's publication through international collaborations. So you see this is the paper collaborated with 2 countries, 3 countries, more than 3 countries. The number of this is the publication number. So you see this is the status. So the publication number with this is the publication number with Chinese first authorship with international collaborators. You see that the Chinese they collaborate mainly firstly with US and then with other countries. The number you see here is the most important. And the 6th discipline of Chinese first authorship in the international collaboration is biology, chemistry, physics. So the physics is listed the 3rd in the whole field of science in the international collaboration. So it's not too bad about physics. Biology is the first. The top 10 discipline of more Chinese ICI publication number, and also the physics is number 4. That means the chemistry and biology, all these things, the number of publication the number is more. But anyway, this is also that's quite good position for physics. So this is comparison of China's scientific output level compared with world average level. So the world ranking is here. So you see it's a rank for physics. It's a rank in the world. If we talk about the output, that means it will count only the number, not the quality or influence of that. Of course, citation has something, but we count the number. Now physics is number 2. Well, this is the country. This is all the domains. This is the ranking. So the scientific ICI publication corresponds to institutional type. So you can see that the university is really a big resource of publication in China. And institutions, this is this number, and so companies here. So the university really produce most of ICI papers. So this is according to OECD, Chinese owned 3-party patent. Is this one in 2014, and this is the 5th place. So according to patent of the US, Chinese owned patent this one, more than 10,000 in 2016. 7% of that of US foreign company patents. So this is also the 5th place. So it's compared with patents. If we compare the patent with US, so this is compared with, so this is not a big number. About the Chinese universities. So you see, we have I don't know this the word. I mean it's not so big. So you see the number of schools, educational personnel, full-time teachers by type and level. So about the graduate student training institution, we have these about and including universities around 800. And among these one, mainly, you see, mainly, most part is university and the institute is about 200. CAS has around a little bit more than 100 institute of Chinese academic science. So the total one is China institution because there are other funding agencies, other channels, totally 200. Okay, so the universities for the normal, in general, this China has less than 3,000. It's 2,500, something like that. Okay, so I will not read all these things. And you can see this is the teacher, the people who in the university is this number. So about 2.3 million of all these universities in China. And about the teachers, it's, you see, is this number. It's 1.5 million. Okay, this is the students, the graduate students. You see, the graduate students in this order. Yeah, so this is 56,000 graduates. Inside there, this is 55,000 PhD, yeah? And so this is the capacity. The whole country, without counting the differentiate. So this is the R&D people number from Chinese universities, and this is the R&D people number from Chinese universities who have all the national R&D people. So this number, see, R&D people number from Chinese universities. And this is the R&D people from the all national R&D people. So this is the R&D fund for Chinese universities. This is 100 million, and this is the R&D fund of Chinese with respect to all nation R&D. So that means this is a measure how university takes this fund, R&D fund. So they are here. So this is R&D fund source repartition of Chinese universities. They come from government, industry, foreign countries, and others. So this is the repartition. So we see mainly from government, but also they have from industry and some foreign. This foreign part is quite small, and some other donations or other resources. So mainly supported by government of this Chinese university fund. R&D fund. So, this is an IFIC publication of the Chinese university, and this is 10K number, and this is the size number of Chinese universities with respect to all publications. So they are quite important in terms of R&D paper, I mean these scientific papers, SAR papers, 80%. So this is patent application universities. This is 10,000 units. It's 10,000, and the patent approved by Chinese university. So they are also it's a source of output for the technology also. About Chinese Academy of Sciences, IGD is belong to CAS, like Shanghai, like Spain, where you have like similar thing. This is a very Russian type, so-called academic science. But these exist before revolution, so-called academic silica. Academic silica, this term is kept till now and in Taiwan. So Taiwan goes to, nationalists goes to Taiwan in 1945, and they kept this name, and CAS changed the name to so-called CAS. And the whole academic silica, this Greek name is kept by Taiwan. Till now, Chinese academic silica experienced these 6 presidents. This is the actually now president now, and this is the first. The first 2, they are politicians. They are literature people, but they are good. They are quite good to govern. I mean, to absorb good people. And they are literal people. From here, they are becoming scientists. I mean, maybe he is a chemist. This is a nuclear physicist. He comes from Dubna. He has been working in Dubna. And a theoretical physicist. And he is an engineer, and this is a nanoscience scientist. Or chemistry. So the CAS, this is the CAS now, this is total number of CAS. IGP is inside. So you can see that this is around 70,000 people. I forgot the Shanghai, how much Shanghai is. Maybe Shanghai, French, I don't know. Shanghai should be more than 10.
The city is about 10,000.
Yeah, more, yeah. I think French should be in the order of 30,000. I will if I remember well. In order, but this is not too big for me, because all the same, for me, this CAS only has this number. Is to my surprise. It's only double the French Shanghai. As I said, it's around 100 institutes near Beijing. In Beijing area, we have around 50 institutes, and in other places another 50 institutes. So we have a PhD, how to say, this is the CAS, personal education repetition. So they are mainly, you see, of course, they have the PhD and graduate education background. And in CAS, this is listed all the so-called large facilities, what we have now in CAS. So we have this monitoring and weather monitoring project, the Shanghai synchrotron facility. This is in Shanghai, this existed. Several GeV machine, and BBC 2, now it's BBC 2 in IFIC. And also, I will not. This is the tokamak. This is the place, Easter, the superconducting tokamak. Recently, they reached, it seems, I don't know, this top number one. Or anyway, there's many newspapers talking about their temperature of this so-called superconducting, so-called Easter. So now they have a project. I think the same amount of budget like a CEPC, they want to construct the so-called CFTR, which is next step of ITER, but more close to electricity plant. ITER is just demonstration. So this is their plant, their plan. So this institute, they have this Easter plant. And this big, China has a big laser facilities in the world. If you accumulate all the powers, and it's a count, I think, number one in the world about laser, high power laser. So the fast, this big, the largest in the world is in the mountain. It's a big satellite in the mountain. All the mountain, this is a huge satellite. Finished 1-2 years before. Almost telescope, Yongbajing, this is I have all the red is I have facility. So this is in Tibet. There are many Italians and Japanese collaborate from many years. Cosmic ray and diamond, this is neutrino, in Shenzhen, this is IGP. And this Hefei signature light source, this light source start in the 80s, still running, they upgraded, and this is XFEL, and China study, this is IGP one, and finished this year in another branch of China, IGP in Dongguan, near Hong Kong, in the source. There have more than 300 people there. And high magnetic field, this remote sensing satellite ground station, this remote sensing aircraft, and other things. So this is the facility list of the CAS, not including other facilities like airplane, this big, huge test wind laboratory. This is not the work of CAS. So this is the Taiwan. So I just show you, but for me it's interesting to look at that. So this is the so-called academic silica in Taiwan, and all these institutes they spread in mathematics, physics, chemistry, and law, and so they have a spread of domain of research. So they have 24 institutes in island of Taiwan. About IFIC, so because CEPC is the host institute is IFIC, so I give you some background of IFIC. So IFIC, in fact, if you look at the history, this is almost the first after the liberation, communist to 1949. And at that time, it's so-called the Institute of Modern Physics, and then it's the evolution from these, and to finally so-called Institute of High Energy Physics, we move it to here. This is during the Cultural Revolution. This university is moved from Beijing. This is a campus of university. You see this building is a Russian style, the Soviet style university style building, and these people moved from Beijing to Hefei in the USTC, in the University of Scientific Technology in Hefei. And so this place gets free, and then inside this is Institute of Atomic Energy. This institute still exists. They are talking about their reactors, and they are not far from Beijing Center. And there's a branch of them to be high energy physics. So they're still, historically they are related. Now these places in nuclear physics, they are cyclotrons, this kind of low energy in nuclear physics. So I have become like that to go to this campus weekend. At that time, this place around is not too many inhabitants, but now it's surrounded already the center of the city. So you see, employee, we have 1,500 people, a student 500, PhD, constant level. Every year we have 100 people intern and 100 people graduated. Visitors and the budget is about, maybe this is not updated, maybe this is last year anyway, this is around this number now. We have Professor Joe is here. Professor Joe, he belonged to IFIC before, and then he moved to theoretical physics as a director. So he's here in the audience. Participate in your community to review something. I don't know, but I'm pleased to find him. So he's a service. So he belonged to this group before. We have a computer center, applied center. So BPC, we have actually the division, and this experimental division, astrophysics, and multidisciplinary. All these people are trying now. They are planning to, not planning. They should start this year at the end of. So the so-called the new light source. I have near Beijing 1 hour and a half drive. This 3 GeV 1.3 kilometer light source. This is a dia May, and then I will show you the new project like June. So this is the background of IGP. So you see, IGP, large science scientific movement from in fact started from 80s. So 83 machine started, and 88 machine. This year is just 30 years of running of BPC. We just celebrated in October, and then the so-called BPC detector is so-called BESS, and we have the electron laser, BFL. This is the first in Asia. So I did my PhD in China period in '86. So I participate to this the first electron laser John Lady type, the select type EMAC-based laser in China. So this is the first lasing laser in Asia. And then you have other things. It's upgraded to BPC2 to RAIN. And this is diabe. This is X-ray. This is satellite. And so this for the future we want to build these, not yet finished. This is light source, Juno, LASSO, and surely there's a CEPC. I think here I miss also the radiation in the Tibet. This is called the Ali project to measure this background of radiation. We try to study this that for the gravitation wave, the collaboration with international station and the other part of the world. So this Ali is in Tibet, 5,400 meters, and from the satellite you see there's a window, there's a hole. So I don't know why there's a hole. So this detector is invented a hole, so very high amplitude. And that project is after discovery, founding of gravitation wave. So this is a facility. Yeah, I say that this is there is it's not complete what I showed that chart. We have ADS, IGP participated to the ADS ejector. Already finished the first CW high current photon beam superconducting, and this one. This is under planning. So you see, this is BPC. This is a BPC2 lane, and they reached this design goal of the university, 2033, 2 years before. And this best three, international collaboration with European, with US, with China. So this is for the best three. And they are making good measurement like precision measurement, how mass, and recently the four-part state nuclei in the proton. So this is the light source. Every year, this machine operates switch to high energy physics and light source. These several. So this is a future light source. 6 GeV. 6 GeV, not 3 GeV. Sorry, this 6 GeV. Very bright, 1.3 kilometers. This diagram you know well. So I don't, this is this is Juno, and this is database here, and if you along the coast, this part, we have two new nuclear plants under construction, and these two nuclear plants, after they finish, we find the optimum place to put this huge detector of the neutrino. There is a list of scientific goal for the mass hierarchy, and also other things. I think main scientific goal, at least the three key ones, I mean, a very important one, at least for 3 and 4 for this experiment. And these underground, now the company is digging, make the hole, and there are some waters, inside, leaking from the underground water. So maybe the project now is delayed by around 1 year now due to this water area, this area, many water in the south of China, mountain area. But in general, this project goes well. Should be in operation in the year around 2020, say 24 or something like that, if I remember well. And this has the deep international collaboration. I will not read this one, so they're quite important. So Professor Yifang Wang is the leading person. He is the IGP director, and he's leading this one. So this is spectral neutron source. So I have this just finished this one. So recently we just decide to update. This is just finished with this neutron goes out like Rutherford, but the power is less than Japan and US. But we want to upgrade this injector by 7 inductive. I mean, to increase the power to reach the second phase. This is the if you go to our IGP spectral neutron source in Hong Kong, so this is the real picture. It's not like Photoshop and design phase. This is the real site. You can see the experimental hall, and this is the main building. Enter here, the parking and the offices and the experimental facilities here. And maybe they will later, they have a reserve of land, this part. And before this area is a mountain like that, and with many trees for fruits. So they erase the mountain and put this laboratory here. This is ADS. As you know, China is planning making many nuclear plants in the next many years, more than 45. I think this number, around this number, not yet built, but in plan more than 40 plants. So there will be many, not like in Germany, so almost nothing. So China's policy, even after Japanese incident, still the momentum is not going down, so so we will produce so many nuclear waste. So to treat all these things, so ADS is one of the solution. Another is this is so-called clean nuclear power plant, that is you produce with neutron and instead of radiative fuel. So in this kind of scheme, if you close electricity, the reactor stop. But all this technology depending on accelerator. So the accelerator is just a very high current photo machine. It's a CW photo machine. So you see the final goal. This is demo of the facility. You inject your beam. So this is 1.3 gigahertz IOC type accelerator for photon. But this part is the cavity shape is changing because the velocity is increasing. The data is 0.2, 0.3, 0.5, 0.8. So now IGP finished this part. Already the machine there at the start. So already reached the design goal. I think that is the first in the world proton beam CW of that current and that power of CW in a very short period. So all the smoke cavities, all the these things. So you can see that is here. You can go to IHAB. Now this machine is stopped now. This is the result they obtained. Also, many technology transfer for this. I don't say too much about that. And they have many pads. And we have a company, IGP company. They occupy this kind of spin-off technology to the society. There are many things. CT. This is Ali. I said. This is actually observatory. This is the attitude of this one. This is approved. This is for the shower observatory. This is Lasso. This is not this is in Sichuan, I think. Another place is better place, so they are working on it. The construction started to get. So about the space program, IGP is a key player in space, and so this is the hard X-ray. This telescope launched last year. Now it's working in space, and there are also other projects. It's under study. Also, this Aura is already launched 2 years before. This is HERD. This is a bigger one. So I have people. They are working on this satellite. It's so-called HERD, and to be launched in 2023. So this is a comparison of Earth and other projects, satellite. And you see the performance of these is quite good in terms of the project. So I almost finished. Sorry for so long time. This is the future plan of IFIC. And you see CEPC is here, and the operation, and the SPPC preparation, and the construction. To see whether it's, this should be the operation. So you see quite a spread of project. So this is the IGP human resource evolution, so something like that. I quickly read the IGP publication number. the annual number of paper published by IGP, you see around this number of peak is 1,000, 1.5 thousand. And this is the SAI cited EI paper. There are some oscillations. This is IGP International Collaboration publication. Evolution. So the collaboration paper is not a small number. The top IGP top 10, top 1 publication field distribution. You see, surely this is physics, and there are many others: mathematics, biology, human space, chemistry. Because IGP working on even the pharmacology and the taxology, nanoscience in this field. We produced a academician recent last year. These are high IGP patents. So you see, this is this year, last year, but before it's quite small. And then increase this patent. You see, the IGP is located in the world. These big institutes, the BMP, FME, KK, SLAC, I have this here. So this is an ICI publication among 8 international labs. So this is the position of IFIC. Now, BNL is, they are quite wide. BNL is quite powerful. This is the ICI public research field versus 8 international labs. So slowly, you see the Brookhaven, CERN, DAISY, IHAB, SLAC, KK, and the BIT. So you see, mainly these labs surely work on the physics. If we compare physics, IGP is here among these institutes. This is IGP scientific among 8 labs. So IGP where it is here. These IGPs, I say publication among them. This is so this is anyway. You can relative number. You can see IGP is here. The 8 international labs, international collaborative group publication. This is IGP is here. IGP versus 7 international patent. IGP is here. Okay, summary. I think I have tried to give you I did not talk about industry, Chinese industry. So this is about the scientific part. So I will not read this one, but I say that the CEPC, Chinese and China's economy is healthy to support future lifespan, like CEPC. R&D investment steadily increasing now, and we hope in I don't know how many years can reach this level, like Israel. But it's difficult. I mean, as a whole country, this one will be a huge number. China science and technology identity ranking in the world is important. As I show you, sometimes it's number 2, sometimes number 4, depending on. And university researchability is very important. Training young, because every year China university produce 8 million university students, around 8 million. So every year they are put to the market. So we need to create new jobs. So more than every year the government have a goal to create a new job of 11 million or 12 million new job. So you see, these 8 million new blood, they are going to marketing. Some people, they go to course, some people go to graduate. But if you look at this moving, I mean, you see this new position and then the new graduate is almost matched. I mean, 11,000 and 11 million and 8 million. You see, you have to match this number, otherwise these people, you'll have problem. So SCARS and I have possessed an important number of large scientific facilities with an output level significant with collaborations. Synthesizing an international project with China could be realized. Personally, I hope as planned. And so thank you. Finally, I will show you a video of how I do that. Four minutes, just for fun. This is not an artistic video. This is a real mechanical. I mean, the installation of components by the company. We provide the design data and the components to put on the tunnel, and all the components we see is a real component. Because it's 100 meter, we put 100 components, so the data is very heavy. Normal computer cannot move, I mean, it's too heavy. So they have to use special techniques to discharge, to lightening this data, and then make a video to be visible. So this is the LINAC power source gallery underground. Below that is the LINAC. This is the power source. This is the LINAC. So the electron goes out from the gun, accelerated in this tunnel, and it hits a positron source. Here, you see it's becoming red, so the positron is produced. It's accelerated. Because positron is big emittance, so we need to damp the emittance in the damping ring, and then to re-inject into the main LINAC to accelerate it until 10 GeV. So this is it goes to underground. So this is a two pipe, one for the positron, electron. So now enter into the tunnel, and then the main tunnel. The main tunnel you will see has the upper one. This is the booster, and this is the main collider. And this picture shows where they are showing this part is here. This is the RF of the booster, the IOC type. So this is the RF of the main ring. This is 650 megahertz, two cell inside. This is the power source and the cryogenic system. This is the classroom for the 650 megahertz high efficiency classroom. Because these two pipes, they're not slide here. They are two pipes. Now we are going to the detector region. Now this pipe is from the booster down, injected into the collider. So you see from the roof to the bottom. And the dipole is very long. It's 6 meters long. And the booster is going outside of the detector part. So it's going to another tunnel, And this is the detector region. We have two. This is a booster bypass. I mean, it's a pass-through booster. This is the tradition of the kind. This is the Higgs we are trying to produce. Okay, so this is the company who helped us to build this. We have two films. One is better, one is less. I do not show you the So thank you very much. Sorry for so much.
Thank you for this glimpse inside the project, literally. We have time for a few questions. One.
Okay, thank you, G, for these impressive figures. I think that you must be very happy, not only because of the absolute numbers, but also the tendency, which is really very positive. I have a few comments, maybe many, but we can discuss them offline. But with respect to the project of the CEPC, I mean, how you plan to include also international participation? And that also in a way which complements the other projects worldwide. I mean, how that can go, how can you make it compatible, how you are planning that, because also you're very aggressive in time. Also, that is how you are managing all this, because you can feel that they will become real.
So very good question. So two questions. The first one, how to incorporate international collaboration. So this morning, I think Marcel was, I have, you were there. Yeah. We had an informal IB meeting, including the international people, Italy. Anyway, now we have IB, but this is Chinese IB. We have, and personally, I'm vice IB chair. This IB is Chinese Institute and Universities. But this in November, we had a meeting with some representative of the worldwide, and we participated to this IB meeting with one of the subjects to discuss this kind of organization, which maybe will change the name of IB. Instead of so-called IB, we change into International Collaboration Board or Committee or something like that. So this morning, I received a document, so-called CEPC MOU, written by an Italian, I forgot the name, and he drafted a framework of international collaboration on CEPC. There's items how the international institute coming and how this committee will assign the directors of CEPC with international participation with their vote. So we have a draft just received. You see, this is working, just the thing. Also in November, after CEPC workshop, we have IAC, International Advisory Committee, chaired by Yongki. So this year, Barry, he was not there, but many people was there. Yanni and many people, Chevalier, Brian Foster, these people there. And they just sent back the final version of the IAC report of this year. So in this year, in the IAC report, also they gave us, of course, this is IAC, this is not but inside this report they give us a request and for action. That means we have to, in terms of action, for example, because they agreed us, the CEPC actuator, we can go to technical design report phase, but the detector part, even finish the CDR, the detect part is not ready to go to TDR, wait a little time. But in this document, they ask the actuator to form international advisory committee And this IAC, there's an International Advisory for X-ray Committee, and we have to report to them, and then they supervise and also give us advice, and then every year they will write their own report to IAC. That means IOC will listen not only from us, they have to listen from this committee about the situation. So they are very, the IAC getting to be very serious and hard to supervise or to all this. So now this is just starting. So what I want to answer the first question is first from IB, from the international body. We are trying to form an international, so it's a good opportunity. Not yet, we're working on it. About the second question, you say there are many, there are other international projects. There are, for example, IOC. Imagine IOC happens, positive next year. We have China will participate to IFIC. This answer is from community, from our Fred Mountain meeting, strategy meeting many years before. We have written conclusion, also some contribution number from that meetings. At that time, it says 5% in the document. So the Japanese ICJ, they know our meeting results. So this feedback is to Japanese ICJ committee. Also, IFIC wrote a letter for this ICJ meeting. I think if other directors done it also, but I did not see other people's letter. But in the letter, IFIC wrote representing to Chinese scientists, not governments. So he gave a number quite encouraging. Imagine if IOC participated. China's participation number is higher than what I cited in the previous number. So, but this is he's not government people, so he just say as willingness as a director. So this is a CEPC. We will imagine we try to have 20 to 30% of international participation. This is welcome, wide open. But I don't think this is a precondition for CEPC to go forward like this. I don't see, I don't know the number. So I don't know if I answered the question. But with Sir, we are talking about Chinese participation as associate member. This year in September, Fabiola visited IFIC, visited most, discussed about these things, and associate member saying these. Personally, I propose to government also, anyway, the most react very positively. They have whole meetings in IGP to listen to the young people, old people, they change. So no guarantee, but this is under discussion. So this, I think this is very good. So the reason why, Fabiola, she visited China in September. So if you have time, occasion, you can ask her about some. But this is not sudden. But I think during discussion we talk about how to collaborate with CERN. Not to see it, but the CERN is highly reliable and upgrade the detectors. Yeah.
In fact, I have, can I make a couple more?
Anyone else, then yeah, go ahead.
Also, on the local side, I understood that there is a process in order to, because CEPC is not yet approved, as far as I understand. And there is a process in which it's also competing with other scientific projects. Can you tell us, I mean, how is the situation?
Very good question. I did not mention this. I should, but I forgot to put this on the transparency. So in fact, the road for CEPC, not necessarily for us, that is a similar project. Imagine we have several, the same scale. Not same, not this is small scale. It's not the same scale. And in the field, they are not necessarily all in the metal field. They might be in life science and other field, energy. Or imagine we have 5 fields. And we already established the 5 committee. The committee member already defined, we know, obviously. And about these 5, we have the leading person and the vice leading person of this 5 committee. And these 5 committees have a matter science. For example, CEPC will go into this committee. And the leading person of this whole committee is the former most minister, who was the most minister of most in 2005 when China participated in ITER. So he knows the ITERs. He administrated this Chinese commission. And there's a vice deputy of him is the so-called Professor Zhang Jie. Is before he belonged to CAS, and then he spent more than 10 years in Shanghai Jiaotong University as dean, and he is a laser physicist, and he is very supportive to CEPC also. But anyway, we have already this body, and their goal is to choose among the applicants, because we have 5 lines. IGP will go to 1 line. And the other people, for example, the energy people will go to another line. On the metal line, I don't know how many people. I don't think there are many, but maybe they can put a few. And this committee will select, in total, 3 or 5 to help them to make progress. That means fund them as pre-phase, construction phase. The government already delivered a plan. The government formally delivered a plan in March of this year. How to do that? That means the road, the administration road already paid. So they say, we will have committee and we will select the 3 to 5 projects as a preparatory project. And after 2020, we will select among them 1 or 2 to construct. And this is the status. That means it's good because before, if 1 year or 2 years before, we don't know the road because this huge project never happened in China. So no organization has a right to decide. Now these are the road has been designed and formed. And most is the key place to handle all this. But imagine 1 or 2 so-called put to construction, I think at that time will be another bureau of so-called China Development Bureau, maybe take over to fund. So this is the state. So now, what we are doing now we are we wrote the proposal to send to these committees. They will discuss, and if CEPC is selected, and we will have in the next several years have a fund for as a preparatory project, because this is overlap with our TDR. But even without this money, we already have other channels quite necessary. So this is the statement.
Last question.
If anyone else wants to ask, we should give them a chance to. No, okay, back to you.
Well, I was impressed by the patterns that you are producing. I mean, you really have a peak, which is something, for instance, here in Spain is the opposite. I think when there were these plans in which there was a compromise to promote science, the number of publications, scientific publications really increased. I think we have a good level on that, but on the number of patents, it is a subject which in Spain has not been well resolved. And in fact, the number is low. And for you, it's just the opposite. How do you manage?
I don't know. I don't think all this patent is useful and good quality. But we experienced in our everyday life, we experienced applying some patents. Of course, we can contribute to this number. But if we just talk about, we don't know the quality of each of these things. But if we really look at these numbers, it's really quite impressive. So personally, I have no measure how useful it is and what is the level of use. But for the first step, we need numbers, and later maybe the quality should be better. But this is due to the government always make pressure to the scientific community to produce a spin-off. So maybe this is the result due to this policy. We have changed the law in China about modified the law 2 years before. I participated to discuss this law. That means transfer of technologies, trying to apply to this, and how to make the scientists benefit from this process. So the Assembly passed a law 2 years ago, which is a good law. But I don't think now this law has already reached the level of institute. Imagine how these transfer technology to the industry, or the kind of how they can, what portion of what can be really connected with the scientists. I have never, till now I did not see, but I see the law was passed, and it's a good law. So I think China government is trying to make these things function and make it works. But still we're not like US or other countries. We are still trying to find the road, especially policy road, because before all these things, nothing to do with scientists. Scientists in India, so they have no motivation. We have a branch in China, IGP, to occupy all these so-called PET and scan and the radiation detector. All these things are good products, but it's really not in Australia for IGP. This is not the main battlefield. So it's the output of this in terms of gain. I mean, it but as a nation, this is pressure. I think it's constant pressure. So maybe this is good.
Okay, thank you very much. I think we should stop here and wait for lunch. Thank you very much.
Yeah, thank you.